Wave Transformer is a vintage-voiced, voltage-controlled oscillator with over 8 octaves of accurate pitch tracking. It is 100% analog and has 7 simultaneous wave outputs, including a unique, complex output. The transform control morphs from a basic waveform through many strange iterations into a complex, gnarled mass of audio mutations. You can yield countless variations on these mutations by combining this novel circuit with hard sync, soft sync, linear FM, and exponential FM. Additionally, you can mute the source waveform to use the circuit as a harmonic gate or VCA. If that is not enough, there is a shape insert that allows you to transform external oscillators and modular-level audio sources. The Wave Transformer is 20 HP wide with a max depth behind the panel of 1 inch or 25.4 millimeters with the power header installed, which makes it very skiff-friendly. The current draw is 90 mA max from the positive 12-volt rail and 90 mA max from the negative 12-volt rail. The Wave Transformer has a lifetime warranty. Now that we have covered all the basics, let's dive into the panel controls, inputs, and outputs. The tune knob provides coarse control of the pitch of the oscillator, spanning approximately 7 octaves. The fine-tune knob gives control over a little more than 1 octave. The MicroTune knob gives precise control over approximately 25 cents. The pulse width control varies the pulse width of the rectangle output between 0 and 100%. At 0 or 100% pulse width, the rectangle output is silent. The transform control morphs the complex output from a triangle wave through multiple iterations into a strange and harmonically complex waveform using an asymmetrical multi-differential audio transmutation circuit. It will vary from a simple waveform to a waveform that resembles the silhouette of a cat when viewed on an oscilloscope. The sub-octave switch selects between 1 octave down, 2 octaves down, or muting the sub-octaves. This control affects the complex and subsquare outputs. The sub-pulse output is unaffected by this control, as it is fixed to 1 octave down. The complex source switch selects between muting and unmuting the source wave for the complex output. Leaving the source wave unmuted allows you to hear the waveform morph from the original wave through multiple iterations until it reaches maximum harmonic complexity. Muting the source waveform means the complex output will be silent if the transform panel control is fully counterclockwise and no CV is present at the transform CV input. This allows the transform circuit to act as a harmonic gate or VCA. It will go from silence to increasing in volume and harmonic complexity as the panel control or CV input increases. The sub-source switch selects either the internal oscillator or the signal patched into the shape insert jack for use in generating sub-octaves. This affects the complex, sub-pulse, and sub-square outputs. Leave this set to internal unless you are tracking an external source. In this patch, we have the wave transformer and an external oscillator tracking a sequence tuned to different intervals. The output of the external oscillator is patched into the shape insert on the wave transformer. All of the outputs produce a signal that is plus minus 5 volts, except for the transform output, which is capable of producing signals up to plus minus 10 volts, depending on the source and settings. All outputs are conveniently located on the bottom of the module. Let's listen to the different waveforms with this sequence. We are currently listening to the sine output, which is the most basic waveform. It sounds smooth and clean, and is made up of only the fundamental frequency. The triangle output has a little bit more buzz to it and contains a combination of the fundamental frequency and odd-order harmonic frequencies that taper off rather quickly. The saw output is a negative ramp saw. It has an even buzzier sound than the triangle and contains a mixture of the fundamental frequency and both even and odd-order harmonic frequencies. The waveform present at the rectangle output is dependent upon the setting of the pulse width knob. Currently, the pulse width panel control is set to noon, so we are hearing a square wave from the rectangle output. The sub-square output produces a square wave that is either 1 or 2 octaves down from the source signal depending on the sub-octave setting. The source signal for generating the sub-octaves is selected by the sub-source switch. When set to internal, the sub-octave is derived from the internal oscillator. When set to external, the sub-octave is derived from the signal that has been patched to the shape insert jack. The selected source will be the same for both sub-outputs. For both the sub and square pulse, we intentionally used an unprocessed version of this output, rather than one that was reshaped using a comparator circuit. It has a sound that is more raw and aggressive. The sub-pulse output produces a 25% duty cycle sub-octave that is 1 octave lower than the source signal. This output is fixed at 1 octave down and does not respond to changes to the sub-octave panel control. The complex output is a strange and novel output that varies between a simple waveform and a complex transformation of the harmonic structure of the original waveform. It contains a unique mixture of the fundamental frequency, odd-order harmonics, even-order harmonics, and subharmonics. Please note that this output can get much louder than the other outputs. Now we are going to explore the inputs on the wave transformer. We've already made quite a bit of use of the volt per octave input. It accepts traditional volt per octave CV to control pitch with over 8 octaves of accurate pitch tracking starting with A-1. Let's add CV control into the transform CV input to enhance our sequence. The transform CV input accepts control voltage up to plus minus 5 volts. This CV input is added to the transform panel control. Use the panel control to set the default transformation from which you'd like to modulate. This input has an inverting attenuator located above the input jack. When the trimmer is fully clockwise, the CV passes unchanged to be mixed with the panel control. When the trimmer is at noon, the CV is fully attenuated. When the trimmer is fully counterclockwise, the CV is inverted before mixing with the panel control to result in subtraction. Transform can be modulated with DC control voltages and audio signals. Switching the complex source switch to mute allows the transform circuit to act as a harmonic gate, or VCA. Volume and harmonic complexity increases as the CV increases. The effects are relative to the setting of the panel control, with the signal muted when the panel control is fully counterclockwise and no voltage is present at the CV input. Now the Wave Transformer is joining with subtle modulation to the transform CV input. The Afterneath module is adding reverb for a little ambience. Now we are using random fluctuating voltage from the Wogglebug to modulate the MicroTune input. The MicroTune CV input is capable of accepting control signals up to plus or minus 10 volts. This is a far less sensitive exponential CV input that allows precise modulation of the oscillator pitch. An increase in voltage of 10 volts will increase the pitch by around 7 semitones. This input can be used to sequence precise pitch bends, add pitch instability with a random voltage source, or sequence tiny changes in pitch for drone or microtonal music. This CV input is added to the pitch panel controls and is accompanied by an inverting attenuator. In this patch, the Wave Transformer is being sequenced by the ground control from endorphins. We will introduce a rising ramp into the MicroTune CV input to achieve a precise pitch bend during the sustained note of the sequence. In this patch, we will listen to what happens when we send a sine wave into each of the linear and exponential FM inputs. We will also see how the FM interacts with the transform control. The linear FM input can accept signals up to plus or minus 5 volts. It allows linear frequency modulation, where an increase or decrease in control voltage increases or decreases the pitch of the oscillator in a manner that has a linear relationship to the incoming voltage. The exponential FM input can accept signals up to plus or minus 10 volts. With each volt of increase at the input, the oscillator's frequency will double. Each volt of decrease will cause the frequency to be reduced by half. The input is DC coupled to allow the use of voltage offsets, audio rate signals, and everything in between. In this patch, we will introduce an LFO into the pulse width CV input jack. This input accepts control voltages up to plus or minus 5 volts. It allows control of the pulse width of the rectangle output from 0 to 100% duty cycle. Pulse width can be modulated with DC control voltages and audio signals. Note: settings of 0 or 100% will result in silence at the pulse width output. This CV input is added to the pulse width panel control. Use the panel control to set the default pulse width from which you'd like to modulate. This input is accompanied by an inverting attenuator that is located above the input jack. When the trimmer is fully clockwise, the CV passes unchanged to be mixed with the panel control. When the trimmer is in the noon position, the CV is fully attenuated. When the trimmer is fully counterclockwise, the CV is inverted before mixing with the panel control to result in subtraction. The pulse width can be modulated to create silence when you do not wish to hear a note, bypassing the need for VCA in some instances. You are now hearing a modulated waveform from a buccal at 258T patched into the shape insert jack with reverb from the afterneath module. The shape insert is an audio input allowing another waveform or modular level signal to be mutated by the transform circuit. The new waveform changes the results heard at the complex output. The sub-octave circuit will track the inserted signal if the subsource switch is set to external. Otherwise, the complex output will have a mixture of harmonics derived from the external audio and sub-octaves derived from the internal oscillator. Lots of strange and interesting results can be achieved with creative combinations and cross-modulations with external sources. Now we will show linear FM without a sequence. now Exponential FM. Now we will demonstrate the sync inputs. The hard sync input accepts plus or minus 5-volt audio signals and uses the incoming signal to reset the phase of the oscillator. This input will work best with waveforms with narrow peaks or pulses. It can use the signals that are either positive, negative, or bipolar. The positive and negative signals will reset the oscillator to different points in its phase. Using bipolar signals will alternate between resetting the oscillator to the two different phases. Incoming transients will force the oscillation period to be tuned to integral multiples of the incoming signal. Now we are hearing a negative pulse. Now we are hearing a bipolar pulse. The soft sync input accepts plus or minus 5-volt audio signals. Positive signals at this input will cause the upper peak of the waveform to prematurely change direction, while negative signals will cause the lower peak to prematurely change direction. Sync tracking is highly dependent on the characteristics and frequency of the incoming signal, as well as the frequency of the wave transformer. Here it is tracking a positive signal. Here it is tracking a negative signal. And finally, here it is tracking a bipolar signal. That's a wrap for all of the features of the Wave Transformer Transfiguration Oscillator. It is a powerful and flexible all-analog oscillator with a unique wave transformation circuit that processes internal and external waveforms and has tons of inputs and outputs. It is a fantastic core to any Eurorack modular system. To learn more or find a dealer near you, go to EarthQuakerDevices.com.